The example we're going to be looking at in this video deals with chocolate cakes because I really like cake. An experiment was conducted to determine the effect of baking temperature on the quality of 3 recipes of chocolate cake. So we have 2 factors, the temperature at which the cake is baked at and the 3 different recipes being used. 6 different baking temperatures were considered, between 175 to 225 in increments of 10. This is a numeric variable, but we're going to treat it like it was just a factor and ignore the fact that they're increasing temperatures as they go up. What they did to conduct the experiment was it would take a long time to go through and make all these different cakes individually. So to save themselves some time, they created 45 batches of cake batter using these 3 recipes 15 times in a completely randomized order. So they created 45 batches of cake batter, kind of randomly assigned the cake batter a recipe, and if that's all they did, this essentially would be a completely randomized design. But they're also interested in baking temperatures, so each large batch was enough for 6 cakes, coincidentally, and each of those 6 cakes were randomly assigned a baking temperature. And after the cakes were baked, the breaking angle of the cake was recorded. What it looks like is we have these 3 different batches. Each batch had a recipe A, B, or C, and each batch was then randomly split up into enough to make 6 cakes, and each of those 6 cakes was randomly assigned a temperature. So this would be kind of a rep 1, and they repeated this 14 more times. So that way we have a total of 6 times 3 times 15, or 270 cakes that were baked and measured using these 3 different recipes and 6 different temperatures. If we want to analyze the data, we can read it into R. And if we look at the data as it is now, the recipe was assigned 1, 2, or 3. The replicate was assigned 1 through 15. And the bake temperature was assigned 1 through 6. And then we have our response variable, the break. Well, the number system is a little unintuitive, even if they're treated as a factor. So what I did next was I changed cake recipe, kept it as a factor, but we'll just label it A, B, and C. So now level 1 will be assigned the letter A, level 2 B, level 3 C. And if we look, we can see that the levels are now A, B, and C instead of 1, 2, and 3. And we can do the same thing for the temperatures. We'll say that the cake bake temp is 175, 85, 95, 205, 215, and 225. And now if we look, it changed these to symbols that are a little more intuitive to understand what the particular level for that factor is. The problem that we have with the data as is, looking back at it, is there are a total of 45 different batches, but this replicate is the indicator of the batch, only goes from 1 through 15. And if we leave it as is, R will think that this batch number 15 for factor B, or level B for factor recipe, is the same as this batch 15 from recipe A, even though they are 2 distinct batches. We want to specify that these batches are all unique. What we can do then is we'll create a new factor within cake called batch. So we'll paste the recipe and replicate together, separate it by a dot. So that way it'll say A1, A2, B3, B4, C13, C14. That way each batch is now uniquely identified. And if we look, that's what we get. A1 through A15. C1 through C15. Now we have 45 distinct batches. You can go through here and double check that all of your variables are what they should be. We want everything in here to be a factor other than the angle. And if we check, angle is numeric, everything else is a factor. And it's always a good idea to start off when you have 2 different factors to create an interaction plot. It gives you a visual representation of kind of what you can expect going into the analysis of the experiment. So we'll let the factor on the x-axis be baking temperature, the trace factor be the recipe, and then the response variable is going to be the angle. We'll have the lines being drawn being our 3 different colors. I put bake temp on the x-axis, so that way we'll have 3 lines, 1 for each recipe, instead of 6 lines, 1 for each baking temperature. You can do it the other way around if you like, though. If you run it, we get our interaction plot. And at first glance, it appears that interaction should be necessary because these lines overlap a lot and intersect. But at a second glance, it doesn't really appear that there's all that much of a difference in the break angle as far as the cakes are concerned. There's a bit of a difference at 215 for recipe A, but overall these lines are sitting on top of one another fairly closely for all 6 different temperatures. So it doesn't really appear that recipe has much of an effect on just the break angle alone. But these lines do increase as the temperature increases, indicating that there does appear to be effect of the temperature on the break angle. At least between 175 to 225, the higher the temperature, the larger the break angle. If all we want to do is analyze it, we can do that pretty straightforward using AOV. We'll say angle is going to be based off recipe times bake temperature, so that way we include our interaction term between the two. The error term that we want to include is the batch. From our 45 distinct batches, the data is stored in cake. I'm just going to call it M0. If we fit the model, and then we ask for the summary, R smart enough, it knows where to put the factors as far as the error terms go. Essentially, R is going to create 2 different ANOVA tables. One where our error term is for the batch, and then one where the error term is for the cakes. And it's going to stick the factors in the correct table. If we're looking at the batch as our error term, the recipes were randomly assigned to the batches. So that means the recipe should be in this ANOVA table, and it is. We have a total of 45 different batches. If we take 2 plus 42 plus 1, we get our total of 145 batches back. So the degrees of freedom are correct. And looking at it, doesn't appear to be any sort of evidence that there's a difference across recipes as far as break angle is concerned. And as we said here, these lines are stacked up on top of one another pretty closely. Recipe A is a little bit more different than B and C are from one another, but overall, lines are pretty stacked on top of one another, not much of a difference. And then if we look at the error within, essentially the error between the cakes instead of the error between the batches, baking temperature was randomly assigned to the cakes themselves, so we would want baking temperature to be for the residuals in the cakes. We had 6 temperatures, so we ended up with a degrees of freedom of 5. And we end up with a really large F value, a tiny P value, so strong indication that there's a difference in the baking temperatures on the break angle, supported by our interaction plot here, because there's a large difference at the break angle between 175 and 225. So at least those two are different from one another. And then if we look at our interaction term, 2 times 5 gives us our degrees of freedom of 10. We end up with an F value of 1. And if the null hypothesis is true, you should end up with an F value close to 1. And we end up with a P value of about 0.44, indicating no evidence of an interaction between recipe and baking temperature. If that's all we're interested in, just want to test to see if they are different, we came to the conclusion, no strong evidence of recipe affecting the break angle of the cake, but really strong evidence that the baking temperature does affect the break angle of the cake. And for these 6 temperatures looked at, it appears to be a fairly linear trend. And what we can do is we can look at each of these designs individually. So if we're looking at a completely randomized design just for recipe, ignoring the baking temperature, we can fit the same model, just remove this bake temperature from it, and essentially what we have is a completely randomized design using subsampling. If we fit our model, we can see that we get the exact same result that we would have gotten from our split plot design when we included baking temperature. So the p-value 0.718 is exactly the same because our sums of squares are exactly the same. And what ends up happening to this within down here is it's going to take the sums of squares for bake temperature and the interaction term and just add them to our residual sums of squares for the across cake the across cake differences instead of the across batch differences. Kind of emphasizing that a split plot design for the whole plot is just a completely randomized design with subsampling. We can do the same thing for a randomized complete block design, ignoring recipe, just looking at baking temperature. We'll fit the same model that we had, just now we're deleting recipe. And if we look at it, then what we end up having is we have the same sums of squares for bake temperature that we did earlier, but the degrees of freedom are different, and the sums of squares are different. What ends up happening is, since we're no longer including this interaction term between recipe and bake temperature, its degrees of freedom get added into the residuals, and the sums of squares for bake temperature recipe interaction get added into the residuals, which changes the F value in our case a little bit, but overall the results stay the same. And again, you want to think of a split plot design as kind of a two-step process. You have one experiment for the whole plot and its factor, and another experiment for the subplot and its factor. The first one is usually a completely randomized design. The second one is usually a randomized complete block design. Skipping over the model diagnostics, what we can do next is we can check to see where the differences in baking temperatures lie. Well, what we can do is, since there's not an interaction term, is we'll refit the model without it, because the function we're about to use doesn't like it if the model has an interaction term, but you're not using it in your follow-ups. Because the effective batch is treated as a random effect, it's better to use a function in R that's better designed for random effects, so I'll use LMER inside of LMER test package. How you fit it is you have the same thing that we would usually. Our response variable by, we're not including an interaction term this time, so we'll say recipe plus baking temperature, plus this part tells it that we want to include a random effect. That's what this one says, is we're basically just going to fit a random effect per batch. And then the data stored in cake. I called it m.noint because we don't have an interaction effect. And then the function we're going to use, located in the multcomp package, is GLHT, which stands for General Linear Hypothesis Test. It's a really general function. It's really flexible, has a lot of options, which makes it look intimidating at first. But it can handle a lot of different comparisons that you want to make after your overall hypothesis test. What you want to do is, if you want to use this GLHT function, is you want to give it the model that you fit, and LINFCT is going to basically say which comparisons you want to make, equals. Usually what we would do is you would give it a matrix of contrast that you'd want to compare. But if we just want to compare all 6 baking temperatures to each other, you can use MCP, which stands for multiple comparisons. We want bake temp equals Tukey. This Tukey part will tell it that you want all possible comparisons. So 175 with the other 5, 185 with the remaining 4, all the way down. And we'll end up with a total of 5 times 6 over 2 different comparisons, or a total of 15. So if we run PA pair, and if we just look at PA pair by itself, all it's going to do is give you the estimates. It doesn't actually do any sort of inference yet. So it gives you what it's testing and its estimates. But if you do summary around it, then it kind of gives us what we want. So unfortunately, I couldn't figure out a way of giving us a confidence interval, but it does give us our estimate and the standard error. From there, you can form a confidence interval once you know what your critical value is. And if we look where there's a statistically significant difference, it puts these little stars next to it. So that way we can see the pairs, which looking at 15 of these simultaneously can be a little bit daunting. What you can do instead, that if you do CLD, it'll put them in groups. So basically what's saying is that 175 is giving the letter A, 215 and 225 is giving the letter C, and if you look, 215 and 225 on average, those are pretty close to one another. So they're saying there's no difference between 215 and 225. 205 is putting it in a group with 195 that they're labeling B. If we compare 215 with the average of 205, those are pretty different. So they're saying 205 and 215 is statistically different from one another. But 205 is not statistically different than 195. Because those two, if you average these three with these three, those two are right at the same, not statistically different. As far as 185 goes, it has AB saying it's not sure if it should go with 175 or if it should go with 195 and 205. So 185 isn't statistically different from 175, 195, or 205. So this is kind of an easier way than having to look through all of these and figure out which ones are different. Just do CLD, and it'll put them into groups that are distinct. So we have three different distinct groups, A, B, and C. C is made up of the two highest temperatures. B is made up of the two middle temperatures with the possibility of 185. And group A is 175 with the possibility of 185. If you look at the slides, it gives us a formula for the standard error when we're comparing these subplot levels with one another. So the average temperature for 185 versus the average temperature of 215. And then if you want a visual representation, if you plot this up here, it'll create your side-by-side box plots in addition to putting in the groups. So it's saying that these two are in group C, these three are in group A, and this one is off in its own group. These three in group B, and this one's off in its own group. And if we check and run this, we end up with the exact same standard error that the function gave us. So it's calculating the standard error the same way as the slides say, which is what we're hoping to see.